In this video, we're going to look at one more example of using the second derivative to tell us what concavity the graph of our original function will take on different intervals and where its points of inflections are located. As we talked about in the previous video, we know that all this information comes from the second derivative, right? So without reviewing all that stuff too much, let's just go ahead and jump into finding the second derivative. So, to find the second derivative, we first have to find the first derivative, right? So the derivative of this, we see that we have -6 times natural log of some function inside of it. So we have a function here and then another function inside of it, but this -6 is a constant multiple, right? So we don't need to worry about bringing this back into play until after we take the derivative of the rest of our function rather. But when we take the derivative of a function composed of another function, we have to use the chain rule, right? Okay, so let's go ahead and do just that. So know that our derivative at the end of it, we're going to multiply it by -6, so let's leave a little space there so we don't forget it. But when we use the chain rule, I'm going to go ahead and set up the little table that I like to use. So we have natural log whatever is inside, and then we have the function that's inside, right? So let's take the derivatives of these things. The derivative of 1 plus x squared is 2x, right? The derivative of natural log is 1 over that original argument, okay? So what we're going to get is, again, we're going to plug in 1 plus x squared in the parentheses and then multiply this expression times 2x. So we get 2x times 1 over 1 plus x squared, or 2x over 1 plus x squared. Okay? So this is our derivative of the stuff that we took the chain rule of, but like we said, we have to multiply it by -6. So here we get -6 times 2x over 1 plus x squared. So our derivative works out to be -12x over 1 plus x squared. Okay? So we found our first derivative, but the question we're dealing with asks us information regarding the second derivative, right? So we need to take the derivative of this thing, and we see that we have a function divided by another function, so we need to use the good old quotient rule. Okay? So let's call this top function g, this bottom function h, and let's figure out what we need in terms of, or what we have in terms of our derivatives and original functions. So g, -12x, h, 1 plus x squared. H prime is the derivative of 1 plus x squared, so we know that's 2x, and the derivative of g is -12, okay? And the way that the quotient rule is said with our rhyme and how we plug things in is that we have low d high minus high d low all over the square of what's below. So low d high gives us -12 times 1 plus x squared minus high d low, right? So here we're going to get -12x times 2x. And so that's what we have on the top. And then on the bottom, we're going to get all over the square of what was below. So now we have this going on. Okay? And so now when we get to this point, what we're going to do is we're going to do a lot of simplification and combining of terms just to make it easier for us to deal with what our second derivative is. So we're going to distribute -12 into this parentheses and get -12 minus 12x squared. And then we're going to subtract whatever this quantity is, and -12x times 2x gives us -24x squared, right? And this is still all over 1 plus x squared squared. So here, if we distribute or multiply this negative times a negative, we get a positive, right? So the top part of our fraction now becomes -12 minus 12x squared plus 24x squared. And this is still all over 1 plus x squared squared. So if we do one more simplification, we see that our derivative, or our second derivative rather, when we do 24x squared minus 12x squared, we get 12x squared minus 12 all over 1 plus x squared squared. So this is our second derivative. So just like we were dealing with critical points of the first derivative, or in relation to the first derivative rather, of how those happen when the derivative is at 0 or undefined, we need to take both cases into account when finding points of inflection, because points of inflection can occur when the second derivative is either 0 or undefined. But we know that in a case like this, f double prime of x will be undefined if we divide by a 0 in the denominator. That's really the only case that could occur where f double prime is undefined, right? But I want to say that the denominator of this fraction that we have here is never going to be less than or equal to 0. Now here's why. So if we plug in any number, any real number rather, we're dealing with the real numbers here, right? If we plug in any real number into x here, whenever we square that number, we're either going to get a positive number or 0, right? We can agree with that so far. But then inside of this argument here, we're adding 1 to that number we just got. So if we have 1 plus 0 or 1 plus something positive, this expression inside of here will be positive. So then if we do a positive number squared, we're going to get, again, another positive number. So this denominator will never be negative after we do all this evaluation down here, and more importantly, it'll never be 0. So what that means is we don't have to worry about where f double prime is undefined. Misspelled undefined. We don't have to worry about that. Again, we only need to worry about where f double prime of x is equal to 0. Okay, so let's do just that. Let's set the second derivative equal to 0 and solve for the x values that make that happen. So 0 equals 12x squared minus 12 over 1 plus x squared squared. So do you guys remember when we talked about rational functions, when you guys graphed them in pre-calculus, wherever you may have seen them beforehand? When we're talking about a function like this equaling to 0, we only really need to worry about where the numerator of the function slash fraction equals 0, right? Because if we do anything with this denominator, like trying to move it around to try to solve for x in any way, what we're going to have to do is multiply the denominator through on both sides. And what happens when you multiply something times 0, but you get 0, right? So these two divide away over here. This times 0 is 0. So all we really have left to worry about is this, the numerator of our original fraction. Okay, so let's solve for x in this capacity. Let's add 12 to both sides. So we get 12 equals 12x squared. Divide by 12 on both sides. Get these both divide away to give us 1, so we get 1 equals x squared. We take the square root of both sides to get the root and the square to cancel away. We get that x equals either plus or minus 1. Because if we plug into this original thing that we had here before we took the square root, if we plugged negative 1 in for x, negative 1 squared gave us 1, and similarly for 1 squared giving us just 1. So here we have 2 points of inflection. We have points of inflection occurring for our function at x equals negative 1 and x equals positive 1. Okay? So now what we're going to do is we're going to make our little number line and do our evaluating of points inside of our new intervals that are made using these points of inflection to determine where our function is concave up and concave down. Let's scroll down here a little ways just to give us a little bit more room to kind of make our number line here. So we're going to have something that looks like this. We have negative infinity, and again I put 0 as a reference point, and then infinity. And our points of inflection rather are 1 right here and negative 1. So these are our points of inflection, so we need to find values inside of the following intervals. I'm going to kind of scroll it over a little bit so I got a little bit more room to work. So we need to worry about negative infinity to negative 1, negative 1 to 1, and 1 to infinity, right? Those are our 3 intervals made now between the points of inflection and our original bounds of negative infinity to infinity. So here, I say for negative infinity to negative 1, let's evaluate f double prime of negative 2. Negative 1 to 1, f double prime of 0, 1 to infinity, f double prime of 2. These are very arbitrary choices. You can choose whatever you want to evaluate. I like to keep it relatively simplistic for my own sanity, rather. Really is kind of the only reason why I do those things. But you can choose really any numbers that you want to evaluate. Now, we have those written down for us. So let's do the evaluations of them. So f double prime of negative 2, if we plug negative 2 into our original second derivative, we're going to get something that after we do a little work in our head, we're going to get 48 minus 12 over 25. And this is going to evaluate to 36 over 25, which is positive. So this tells us that I'm going to actually kind of box these in just so we know where our answers are. That was a horrible box. I kind of got everything in there. Let me fix that. Let me do this right this time. There we go. That's better. So we returned a positive value for our second derivative. So on this interval, we are concave up. If we plug in 0 into our second derivative, we get negative 12. And this is negative, right? So our function is concave down. Then what about f double prime of 2? Well, again, we're going to get 48 minus 12 over 25 equals 36 over 25 by nature of all the squares that we had in our second derivative. So this is positive again, and we hit that this is concave up on this interval. Okay? So, like I said, I kind of prefaced this video in the ending of our last video that we did, or the first video for this section, that this one would be a little bit more difficult to take the derivative of, but it was largely using chain rule, quotient rule, a lot of stuff we've already seen, and we got a quick little refresher of rational functions and kind of the different underpinnings of them in terms of where it's zero, where it's undefined, all that kind of good stuff, and got some good conceptual math review inside of the whole denominator not being negative or equal to 0 little bit that we discussed about. So what we did in general, just to kind of sum up and review, we looked at a function, just an arbitrary function that we had, and we used its derivatives. In the 2 videos for the section before this, we looked at intervals where the function's increasing, decreasing, where it has local maxes and local mins. And then we can also use the second derivative to tell us where the concavity of our graph changes, as well as the intervals of where our function is concave up and concave down. So instead of using a plug-in method of plugging in different x's into our original function, coming up with a table of values and making a rough sketch that way, we can now use calculus to tell us, to give us a more general sketch of the curvature of our graph, and it can be even more accurate based on the processes and all the mathematical knowledge that we now know that underpin all of those graphs and all these functions that we've learned about so far.